Hi everyone, we are continuing the third algebra workshop with Emre's speech. It's your turn, Emre.
Thank you. Hi to everyone. My name is Emre, and I'm attending this year Sırrıcalı Anatolian High School as a senior. And I'm going to present to you cluster algebras in an intuitive sense. Can you see my screen at the moment?
Okay.
Okay. The topic of the talk is an intuitive approach to cluster algebra. First, in the outline, I'm going to tell you about first the background information about cluster algebras, and then we're going to mention about the main basic terminology of the special algebraic structures that we need in order to make sense of cluster algebras. And then we're going to talk about Grassmannians and Pluquet coordinates. And at the middle of the presentation, the heart of the presentation, there's the definition of cluster algebra. Then the cluster variables, which are quivers and seeds. And then I'm gonna give you two examples in order to make more sense. Then patterns I'm gonna mention. In the final parts, I'm gonna explain to you how cluster algebras can be explained in a geometric shapes. And this will contain two subtitles, triangulations of a polygon and Stasheff Polytopes. First, we are beginning with the background information. Actually, cluster algebras were introduced as a tool for studying total positivity and dual conditional basis in Lie theory. And it was introduced by Fomin and Zelevinsky in 2002. And since then, cluster algebras outgrown a lot, and they are connected with various fields of mathematics, including combinatorics, representation theory, Riemann surfaces, triangulations of surfaces, and many more. We have a definition of a ring at the moment. Suppose that R is a set, and addition and multiplication are two binary operations on R. Suppose further that our set, which we mentioned here, let's call it A's, A1, A2, and go to AN. This set is associative under addition. This set needs to be commutative under addition. It has to have a zero, that is its additive identity, and then an additive inverse. What do we mean by additive inverse? If it sounds a little bit weird, it's almost the same thing as subtraction, which can people see in high school and before. Then our field needs to be associative under multiplication. Furthermore, our field, the one is the multiplicative identity of the field of the ring and of our set, and it has to have contain one. Then our set, the elements in our set needs to be following the property of distributivity on left and right hand side. If all of these properties are hold, then we can call this set is a ring easily. When we come to the commutative ring, we see that if the multiplication is commutative for that ring is called commutative, and it can be seen over here that A times B equals B times A. If the elements of our set, which we defined as ring before, follows this property, we can call that ring is a commutative ring. So which sets can be given as an example of a ring? There's a set follows these properties, and that set can be given an example such as integers. Integers follow all these properties, and thus it makes an integer set is a ring. In the following part, we have a definition of a field. When we remember all of the properties that our ring had, when we add up our two new properties, which are multiplicative inverses and commutativity of multiplication, we get a new algebraic structure, which is called field. And what is multiplicative inverse, actually, at this instance? A multiplicative inverse is inverse of a multiplication, which can be, you can remember as division. And in that, for every a non-zero in F field, there exists an element in F denoted by a to the negative 1 power, or 1 over a, called the multiplicative inverse of a, such that a times a to the negative 1 power is 1. And in the commutativity, we just seen that if a ring is commutative under multiplication, it's called commutative ring. And here we have two properties. If a set only follows the properties of a ring and commutativity, it's called commutative ring. But if it follows the property of multiplicative inverses, it's also called, it can be called a field. So which sets can be given as a field? When we think about it, rational numbers can be given as a field because they are written like this, and they follow all these properties that I stated in the ring parts and I stated here. So, is there any question until now in the chat box?
There is no question.
Okay.
We can continue.
We can move on. Right now we have the definition of a vector space. Let's think of a set whose elements are called vectors. The two binary operations defined on a vector space that are addition and scalar multiplication creates our vector space. And there's a an intriguing part about scalar multiplication, because where scalars are taken from the field, the vector space is defined on. If we take a scalar from set, let's call it F, our vector space will be named according to the name of this field. And we can see here what is a vector, an example of a vector. Moving on, we have matrix, the definition of a matrix. Every linear mapping can be written as a matrix and has the form, for example, like this. We use linear mapping. Like, what is a linear mapping anyway? A linear map is a mapping between two vector spaces that preserves the operations of a vector addition and scalar multiplication. So, in the last title, we have skew-symmetric matrix. Particularly in linear algebra, a skew-symmetric matrix is a square matrix whose transpose equals to its negative. A skew-symmetric matrix can be represented as this: a to the transpose equals negative a, but also a to the ji equals negative aij. These were all the main definitions. Right now, we'll come to the part where Grassmannians start. Let n bigger or equal to 2 and consider the k vector space V, which we're gonna heavily stand on it. Let's write V here, of dimension n. For n bigger or equal to d, bigger or equal to 1, we define the Grassmannian to be the space of d-dimensional vector subspaces of V. Grassmannian k-dimensional vector subspaces of n represent an elements as k times n matrix. which we can see a k times n matrix that is arbitrarily chosen right over here. And coordinate ring C Grassmannian two-dimensional vector subspaces of D-dimensional vector space is generated by Plucker coordinates. So Plucker coordinates is in the next slide that I'm going to mention. We have Plucker coordinates here. Plucker coordinates are actually arise naturally in geometrical algebra. And we can see here that a representation of Plucker coordinates in planes x, y, and z. We have many of them, and we can add them or add to each other or multiply them with scalars. Now, if we come to the definition of a Plucker coordinate, in a three-dimensional projective space, P to the third power, let L be a line through distinct points x and y with homogeneous coordinates, x through x3 and y through y3. In this special example, actually, there has to be a z coordinate as well. Moving on. The Plucker coordinates Pij are defined as follows. Pij is the determinant of this special matrix, xi, yy, xi, yi, xj, yj. And the determinant can be found by summing up, multiplying this xi to yi and xj to yi, subtracting xj to yi. That can be seen right over here. The Plucker coordinates satisfy this polynomial expression. And this polynomial expression is just looks like the exchange relation. We will see. And the note states that three-term Plucker relation correspond to exchange relations. And in another note, adjacent clusters exchange exactly like two Plucker coordinates, corresponding to the crossing diagonals. And this will be we will heavily stand on this in the triangulations of cluster algebra. Right now, until now, do we have any question in the chat box? Or
We aren't any question. There isn't any question. We can continue.
okay. From now on, I'm gonna explain to you cluster algebras more deeply. First, the definition. For any positive integer n, a cluster algebra A of rank n is a commutative ring with two units and no zero divisors. A is equipped with a distinguished family of generators called cluster variables, which then we'll see as quivers and seeds. These clusters have a property called exchange property. It just looks like the previous slide. We've seen the Plucker coordinates relation. It's just like that. And this is our exchange property that I'm going to mention in a more deeply in the seed mutation part. For any cluster X, there is an element X prime in the same field that our X is defined on. But how can we get X prime? We can use exchange property to mutate our X into X prime. And these both properties, these both elements will be under the field of X. Any two clusters can be obtained from each other by a sequence of exchanges of this kind. Now we've come to the part where I'm going to explain to you cluster variables. And our first variable is quiver. In the definition of quivers, it says that a quiver Q is an oriented graph given by a set of vertices. And we can see that this set of vertices right over here. These arrows are representing our quiver. And what are these arrows? Binding, bonding. The points that our quivers bound are named as nodes. These nodes will be our property that takes the seed into it. And we can mutate the quivers in a basic sense, in 3 steps, actually. For every path, I to k to j, add one arrow, I to j. And in this special case, we have, instead of I, k, j, we have 1, 2, and 3. And then after we name our I, k, j again, we get 1, 2, 3, 4 arrow. So if we like to write this mutation steps, for every path I to k to j, add 1 arrow, I to j, which is 1 to 3. And I'm adding 1 arrow, I to 3. 1 to 3, sorry. Then reverse all arrows at k, and in this part 2. I'm reversing all these arrows. And in the last part, delete 2 cycles. And I'm deleting cycles, which gave us the new graph. The graph that our node into is mutated. And we show the mutation notation as mu in Greek alphabet. Mutation over the same quiver results as the first one. And that can be given example of mu k squared q equals q. Right now, what does this mean actually? We mutated in our graph first our second node. However, if I like to mutate again the second node, I'm gonna, this application will give me the first graph again, just like that, from this to this, by mu 2. And we have a tablet that was created by using JavaScript, and I wanna show it to you. It's a useful tool. Can you see the tablet at the moment?
We can see.
Okay. Right now we have 1 through 10 nodes. And if we tap one of these red bubbles, they will, it will change our arrows. Because if we tap them, we would have been taken their mutation. For example, let's tap 1. It changed the arrows, it reversed them, and it deleted the one that connected 1, 2 to 3. If we tap it again, it turned into the same position again, which which is a proof that our mu squared q equals q. Then, if we can, we could create different kind of graphs, kind of like this, and it's a pretty useful tool for studying quiver mutation to exemplify it. And moving on with the slides. We now have seeds. Seeds will be defined in our, sorry for that, in our nodes that we've drawn. Let's take the part A2, which A2 means there will be 2 nodes, as named A1 and A2. And I chose this A1 and A2 arbitrarily. I could have said X1 and X2. It doesn't matter. This A1 and A2 actually will be our seeds. And when we look at the definition of a seed, a labeled seed in F is a pair QX, where X is X1 through Xn, forms a free generating set for F. Q is a quiver on vertices 1 through n, whose vertices is 1 through n. And there will be 2 types of vertices that we're going to see today. One of them is called a mutable vertex, and the other one is called frozen vertex. Now moving on, we have a seed notation part. Seed mutation can be defined by let K be a mutable vertex in Q, and let xk be the corresponding cluster variable. Then seed mutation mu k qx will go to the q prime and x prime, and it's defined by our exchange relation, which stays right over here. We've seen this exchange relation in the definition of cluster algebra, and I'm gonna explain it with an example that I'll draw right now. At this moment, we see that xk times xk prime, which is meaning that xk is one of the clusters we have, and the xk prime is a cluster that is the mutated xk. We have xj elements of arrows that are xj that the arrows k through j plus xj's arrows that are coming to j. Like what I mean is, if we have arrows that are emitted from k, that are going out from k, and the arrows that are coming to k from the j elements. If you want to give the example of cluster type A2 again, we have two nodes as named x1 and x2. Let's call them this way. First, if we try to find this thing as x1 times x1 prime equals all the xj's that k, which in this case are x1, is going, all the arrows that are going out from x1, which there's one arrow going out from x1 to x2. We write x2 in this part, plus, as it's stated right over here, and plus all arrows that are coming to xk, k, which in this case are x1. Is there any arrow that is coming to x1 at the moment? Like, I can't see any arrows coming. So we write 1. Then this will give us our exchange relation. However, in order to find x1 prime, our mutated seed, we need to divide both sides with x1, and this will leave us with x1 prime equals x2 prime 1 over x1, and this will be our new cluster seed. Until now, is there any question? I guess not. Let's note that arrows between two vertices. Sorry?
There isn't any question. We can move.
Okay. Arrows between two frozen vertices, which I'm going to mention in a minute, of a quiver do not affect seed mutation. They do not affect the mutated quiver or the exchange relation. It will make much more sense in the cluster algebras of geometric type. Right now we have our first example. We have our exchange relation over here, and in this part of the graph, we have 1, 2, 1, 3 going on. These are our seeds. Each of these is our seed, but the ones with the rectangle inside of a rectangle are frozen vertices. They are not able to they are not mutable. We can't mutate them because they are set as they are there. However, these all frozen vertices are connected to one mutable vertex, which is R12, 1, 3. And if we mutate 1, 3, we get 1, 3 prime. But what is 1, 3 prime? It intrigues us that what is 1, 3 prime. If you want to find 1, 3 prime, we can use these coordinates. Let's follow the property of our exchange relation. First, if we want to find xk prime, we divide both sides with xk. Then we follow the procedure. Xk1 3 prime equals to all the nodes that are going out from 1 3, which are 1 4 and 2 3. We multiply them. Then we add new one, which is all the arrows that are coming to rk. In this case, 1 3. And all the arrows that are coming to k is 3 4 and 1 3, 1 2. In the end, we divide the whole polynomial with r1 3. That's the coordinates we began with. And here it is. Our mutated 1 3 coordinate equals 1 4 times 2 3 plus 1 2 times 3 4 over 1 3. And as you can see here, if I kind of clear all the writings, we exchanged all the graphs, all the quivers, like 1 3 1, it was before 1 2 to 1 3, and now it's 1 3 prime to 1 2, and vice versa, all of them. In the second example, we have a little tree. Let Q be a quiver on the vertices 1 and 2, and we mutate these vertices according to a sequence, which is 1 2 1 2 and 1. In this case, we have been muted these vertices for 5 times, and if we follow this sequence, we are left with the same vertices again over here. Like, if you wanna give an example first, I can show you that in the first vertex there's our seed x1. In the second vertex there's our x2 seed. If you mutate the first vertex, which is x1, it will follow the exchange property that we have solved many times. First, is there any quivers that are? Is there any arrows that are coming to x1? No. So we write 1. But is there any arrows that are emitted from x1, that are going out from x1? There's one, which is x2. We add x2 with 1, and then we divide the whole polynomial with x1, our first seed that we began to mutate. And then our quiver will be changed as well. It will be turned in the other direction. If you follow this property, we first mutated our first vertex, and if we mutate the second one again, and then 1 again, 2, 1, we are left with the same one. However, there's a difference between these two graphs. In the first vertex, we have x1 in the up and x2 in the bottom. Like, in order to not have this situation, we can mutate 5 more times following the same sequence, which is 1 2 1 2 1. And in the end, after 5 more mutations, we are left with the exact same graph, that is 1 through the main vertices, and there's a quiver between the vertices. However, in this case, if we ignore the vertex labels, we can say that these are exactly the same, because x1 goes to x2. In this case, x1 goes to x2. Is there any question about this part?
There isn't any question on Mute for chat.
Okay.
We can move on.
Next, moving on to patterns. This is where things get more intriguing. Let T0 be a seed Qx has n mutable vertices. Consider the n-regulated tree Tn a simple undirected connected acyclic graph, which is shown over here. And we used tree of unregulated of type A5. What does A5 mean? We've talked that A2 equals 2 nodes and 1 quiver. And in this case, A5 equals 5 nodes and 4 quivers that is connecting them, that is bonding them. And in this unregulated type of tree, we first choose an arbitrarily a first beginning cluster. After we choosing this cluster in the form of A5 type cluster algebra, then we can mutate 5 different seeds that is defined on our nodes. We can call them x1, x2 through x5. First, if we mutate our first seed, which is x1, we obtain a different graph. If we mutate x2, we obtain a different graph, and so on. And if you mutate the mutated clusters in other sequences of 1, 3, 5, 4, 3, for example, we can get another that much different graphs as well. However, if we mutate our first seed with in the 2, and if we mutate it again in the corresponding to 2, we get our first seed that we began with. Is there any question about this unregulated tree of type A5? Okay. Next, moving on, we have triangulations of a polygon. If we take a polygon, in this special example, we have a pentagon. We can find some diagonals in them, such can be seen like this. We name all of them beginning with the diagonals 1, 2, 3 to 7 in the clockwise direction. Then this will be our triangulation T of a pentagon. If we want to find the quivers inside of our polygon, inside of our pentagon, we can look at the second example, which is can be seen like this. All of the vertices of a pentagon are named white, as you can see, because all of the vertices are frozen variables, frozen vertices. They can't be mutated; they are unmutable. So, however, they're inside, we can see that they are diagonals and they are colored with red because they can be mutated. And these mutations on triangulated pentagon we will call it as flips in the next slide. However, there is one more thing I should mention. Look at coordinates of Grassmannian two-dimensional vector subspace of d-dimensional vector space are in bijection with the set of sides and diagonals of the polygon. And they can be shown like this. We have these points 1, 2, 3, 4, 5, and the vertices between these points are naming our Fluker coordinates. For example, the one with 1 and 2, between the 1 and 2, it's called P1 and 2, P1, 2. The one with between 2 and 3 is P2, 3. And these will these are our Fluker coordinates. Next, we have flips. We've said that we can mutate our clusters, seed graphs, like this. If I mutate the first one and the second one, first one will be prime, and the quiver between them will be reversed. However, if you would like to take this application and apply it to a polygon, you can use the mutable vertices of R, which are diagonals in that pentagon. For any true triangulation is connected by a sequence of whitehead moves, and we call this flip a whitehead move. Each whitehead move replaces one of the flickered coordinates by a new one. We can associate flips with the mutations we apply over clusters that I've stated right over here. And our method is pretty straightforward. We have this quadrilateral here, that our T is one of the diagonals of it. After I labeled this quadrilateral, there's two possible diagonals in this quadrilateral. One of them being as the T vertex of R, and the other one is a possible which can be shown like this. This is another diagonal that we can create. And if we want to mutate our T vertex, T mutable vertex, after mutation, we end up with T prime. That is our other possible diagonal that we've stated in the quadrilateral that we choose. And this is the whole process of flips and the mutations in pentagon. We obtain our mutations in a pentagon by using flips. In the next slide, we have Stasheff polygon, also called as associator. In this particular case, we can associate cluster algebra to Grassmannian, field of Grassmannian. And this can be visualized by using associator or Stasheff polygons in the other name. In this case, we have a Stasheff polygon that is created by using pentagons. And in the pentagon part, we have six-gon geometric shape. And in order for us to find a six-gon geometric shape, we need to have three nodes. Because three nodes, every node will represent a diagonal, and all the possible diagonals inside of a six-gon shape is three. There are three possible diagonals, and all the diagonals will represent seats. In this particular case, we have this six-gon, and it has diagonals that are 1 to 3, 3 to 5, and 5 to 1. If we use our flip that we've just seen, and if we flip the one vertex between 3 and 5, we can get another diagonal that is under the quadrilateral of 1, 3, 4, 5, like this. The other possible diagonal, which is 1, 2, 4. If you flip the other elements, which in this case 1 through 5, we have a special, another geometric shape, and the quadrilateral inside of this diagonal is turning from 1 to 5 into 3 to 6, and we get another geometric shape. And these two are connected as well. If you mutate the one with that is between 1 to 3, we get 2 to 5. And following the rule of flip, which is also mutation, we get a Stasheff polygon that is contains 14, I guess, different shapes. And all of these different shapes are all possible clusters of ours. Is there any question about Stasheff polygon?
Let me check YouTube. 1 minute. No, there isn't a question.
Okay. If Stasheff polygons are clear, we can move on with cluster algebras of geometric type. By using the language Wolfram Mathematica, me and my mentor created some of the three-dimensional shapes of Stasheff polygons in different types of cluster algebras. In this presentation, I'm sticking to the A type of cluster algebras, so I'm going to show you three type of A type of cluster algebra, which are A3, A4, and A5. In the A3 case, we have a shape that is looking like the one Stasheff Polytopes that we see in the previous slides, which is this one. If we take each of the geometric shapes as a point, we have a different polygon, and this equals to this one. So what do I mean by that? Each of these points contains our cluster graph. And in this case, in A3, we have three nodes that is connecting them. And in the case of A4, we have four nodes that is connected to each other with quivers. And each of these nodes are mutable nodes. So we can get another cluster just like this, but in a different seed of each of the nodes that we mutate. And there are many possible mutations, and there are many possible clusters that we can get if we add up the number of nodes we have. In this case, we have 3 nodes. In this case, we have 4 nodes. And in this special case, we have 5 nodes with 4 quivers connecting them. And this creates A5. A5 is the most complicated shape that we can see, because as the seed number goes up, the possible mutations expands as well. And in this particular case, we exponentially create more and more possible clusters, which gives us the potential three-dimensional shape of association in an empty space. And I guess this was all things I wanted to say to you, I want to present to you, and there are citations. Thank you for your patience.
Çok iyiydin Emre, eline sağlık.
Teşekkürler.
Var mı eklemek istediği olan bir şey? Olan biri? Yok galiba. O zaman bir hatıra fotoğrafı alalım. Müsait olanlar kamerasını açabilirse çok iyi olur. Bakalım. Kayhan teşekkür ediyor.
Teşekkür ederim.
Yok mu kamerasını açan? Tamamdır. Böyle. Emre sen ekran görüntüsü alabiliyor musun? Benimki sorun çıkartıyordu.
Yok, ben de alamıyorum.
Tamam o zaman şöyle yapalım. Salih açtı kamerasını. Yok mu arttıran ya? Tamam. Çekiyorum o zaman. 3, 2, 1.
Çektin mi?
Bir dakika tekrar alayım. Yiğitalp sen alabiliyor musun? Benimki sorun çıkartıyordu.
Ben şu an telefondayım ya.
Ben aldım ekran şeyini, görüntüsünü.
Tamamdır. Tamam. Teşekkürler böyleyse.
Teşekkür ederiz.